Dear students, in this video we learn how deadlock avoidance algorithms handle deadlocks. There are two types of resources. Single instance of resource type will be there, multiple instances of resource type will be there. In order to handle deadlocks in single instance resource, we have to construct a resource allocation graph. If multiple instances of the resources are there, we use Banker's algorithm to handle the deadlocks in deadlock avoidance algorithms. Deadlock ignorance algorithm, we use Ostrich algorithm to handle the deadlocks. First, let us look into the single instance resources by using resource allocation graph for deadlock avoidance. In the resource allocation graph, there are processes and resources, and these are connected by edges. So processes are represented by using circle symbol, resource is represented by using square symbol, and this resource and process is connected by a edge. This edge may be a solid edge or it may be a dotted edge. So generally a climb edge is represented by using a dotted edge. P1 is climbing the resource R2. So at any time the P1 can request R2. So P1 is having a climb edge to R2. Similarly, P2 is also having a climb edge to R2. That means in future P2 requests the resource R2 at any point of time. R1 is a resource allocated to P1, so this is an assignment edge. R1 is a resource assigned to P1, assignment edge. P2 is a resource requesting R1, so this is a request edge. So totally three types of edges are there: climb edge, request edge, and assignment edge. Climb edge converts to request edge when a process requests a resource. Request edge is converted to an assignment edge when the resource is allocated to the process. When a resource is released by a process, assignment edge may be converted to a climb edge, because if the resource may be required by the process in future, so it may be converted to a climb edge also. So in this resource allocation graph algorithm, so we need to maintain the requirement of the resources a priori in the system by each process. So consider an unsafe state scenario in resource allocation graph. Now you see that the climb edge by process P2 is converted to an assignment edge because resource R2 is assigned to P2. Previously P2 was climbing R2, then P2 would have requested R2, so R2 is allocated to P2. Therefore climb edge is converted to request edge is converted to assignment edge. Now in this case P1 is a process is climbing R2, it may request the resource R2 at any point of time. So therefore, for example, if P1 is requesting R2, then cycle forms. This dotted line will be converted into solid line. This dotted line will convert into solid line and there forms a cycle. This is a deadlock state in system. So the request can be granted only if converting the request edge to an assignment edge does not result in the form of a cycle in the resource allocation graph. Then only the resource will be granted to the process. Otherwise, it will not be granted to the process. This is considering the safe state condition of the system. So allocation of the resource to a process does not form a cycle, then the resource will be allocated. If it forms the cycle, the resource request will not be granted. One more example for resource allocation graph. Here in the left hand side, it is a resource allocation graph. It shows the allocation of the resources to the process and the request of the processes to resources. That connectivity is shown in the resource allocation graph. We can eliminate the resources in this graph to convert this graph into a wait for graph. So just by taking only the dependency across the processes, among the processes, P1 is requesting R1, but R1 is allocated to P2. That means P1 is waiting for P2. So P1 there is a connectivity to P2. Similarly, P2 is requesting R2, R2 is allocated to P5. So there is a dependency from P2 to P5. P2 is requesting R4, R4 is allocated to P3. So P2 to P3 there is a dependency. So there is a connectivity from P1, P2 to P3. Like that P3, P4 connectivity. So P2 to P4 is also there is a connectivity because P2 to P3, P3 to P4 there is a dependency. So that means it means that, so here there is also one more dependency. This is the dependency. P2 to P5, P2 to R5, R5 to P4. That means P2 is depending on P4. P4 is depending on P1. So again P1 is depending on P2. So like this the connectivity is established and the wait for graph is constructed. In this wait for graph there is a cycle here. In this case there is no cycle, but outer cycle there is a outer cycle. So there are two cycles are found in this situation. So therefore there is a deadlock. So allocation of the resources are in the unsafe state. This is how we find whether there is a deadlock in the system or not, by constructing a wait for graph from the resource allocation graph. So in deadlock avoidance algorithm, generally resource is allocated to a system only if the system is assumed to be continue in the safe state. If the system is in unsafe state, then the request for that particular resource will be denied. Coming to multiple instances of resources, if multiple instances of the resources are available, then we use Banker's algorithm for deadlock avoidance. So in Banker's algorithm, every process must have the prior knowledge about what are the resources it needs for its execution. So it has to list what are all the resources it needs. When a process requests a resource, it may have to wait. When a process gets all its resources, it must return them in an infinite amount of time. That means if a process have all the resources for execution, then it will go for execution. If a process do not have the resources and some of the resources are pending, then the process has to wait until all the resources are made available. Once the process gets all the resources, it will execute and complete and then release the resources for other process to utilize. This is the process used in the Banker's algorithm. The Banker's algorithm maintains four lists, data structures. One is available list, maximum list, allocation list and need list. Available is nothing but a vector. This will maintain list of available resources in the system. Max is a vector. This is going to maintain 2 by 2 matrix. It is going to maintain the maximum resources required by each process for its execution to complete. Then allocation is a matrix. It is going to represent what are all the resources allocated to processes. Need is the matrix. It is going to keep track of what are the remaining resources needed for that process to complete its task. Consider there is an example, 5 processes are there, P0 to P4, and there are 3 resources are there. The resources are A, B, C. These resources are available in multiple instances. A is available 10 instances, B is available 5 copies, C is available in 7 copies. So totally 10, 5 and 7 instances of A, B, C are available respectively. At time T0, this is the scenario in the system. P0 to P4, these processes are in the system. The resources A, B, C allocated to these processes are given in the table, and maximum need of these processes is also given in the table, and after allocation how many resources are available is given in the table. So out of after allocation of the resources 2, 3, 2, so totally 7 resources are allocated to processes. A is 7 resources are allocated, B is 2 resources of B are allocated, 5 units of C are allocated to the various processes. So when we subtract 10, 5, 7 are the original resources available. 10, 5, 7. Suppose if we subtract 7, 2, 5, the remaining resources are 3, 3, 2. 3, 3, 2. These are the available resources in the system. That is what given here in this table, 3, 3, 2. Now, what is the need of the resources for each process? So we compute maximum minus allocation, that is nothing but need for the resources by each process. So we are calculating that need matrix here. So maximum is 753 minus 010. This gives you 743. Maximum 322 minus 200. This gives 122. Likewise, all other entries in this table are computed. Now, in what order these processes will carry out its execution? Now let us consider the step-by-step execution of the banker's algorithm for this particular problem. Now let us consider, initially there are 3, 3, 2 resources are available. So first we are allocating resources to the first process. What is the first process? P1. We are considering P1. P1 is having a need of 1, 2, 2. P1 is having a need of 1, 2, 2. So we are allocating 1, 2, 2 resources from 3, 3, 2. So from 3, 3, 2, 1, 2, 2 are subtracted. The available resources will become 2, 1, 0. So 1 will complete its execution. So after execution is completed, whatever resources are allocated for P1, that is 3, 2, 2 are released. So 3, 2, 2 are added to the list of available resources. So 2, 1, 0 plus 3, 2, 2, it will give you 5, 3, 1. So these are all the available resources in the system now. So when P1 completes, then P1 is completed. What are the remaining resource processes? P0, P2, P3, P4. So next process we are taking the next process which require least number of resources, 0, 1, 1. So P3, 0, 1, 1. So available is 5, 3, 3, but required is 0, 1, 1. So allocation to P3 is carried out. So minus 0, 1, 1. This gives you the remaining resources, 5 minus 0, 5, 3 minus 1, 2, 2 minus 1, 1. So these are the available resources in the system. Now P3 completes its execution. After P3 completes its execution, whatever maximum resources that is held by P3 are released. That is 2, 2, 2. So likewise 2, 2, 2 is added to the list of available resources. Now we will get available resources 7, 4, 3. Now the next, from the 7, 4, 3, which process we can carry out its execution. So in the order of the resources, so next lowest resources required by the process is P4, 431. 431 is the resources requirement for P4. P4 we are allocating 431. So 7 minus 4, 4 minus 3, 3 minus 1. These are all the 3, 1, 2 are the available resources in the system. So P4 completes its execution. Once P4 completes its execution, it will release the resources held by P4. That is 433 resources are released by P4. So 433 is released. It is added to the list of available resources 7, 4, 5. This is the currently available resources in the system. Next we will go to according to the, either we can take P2 process or P0 process, because P2 requires 600, P2 requires 600, P0 requires 743. So we can take any of these two processes in any order. So either P2 can be taken or P0 can be taken. So here P0 is taken here, plus 753 is the 743 are allocated to the P0 process. The remaining balance becomes 002. Now P0 completes, it releases 753 resources. Now the list of available resources have 755. Then P2 will get 600 resources. Now balance in hand is 155. P2 completes, it releases 905. So finally the total available resources will become 1057. That is nothing but initial capacity of the resources. So 1057 are the total resources available that will be made available at the end of the execution of all the processes. The sequence of execution of these processes is P1, P3, P4, P0, P2. Another sequence is P1, P3, P4, P2, P0. Like that, there are various sequences may be possible for this particular example. So all the sequences are valid sequences only. So whichever sequence completes the execution of all the processes, we have to take out that sequence into consideration. Next, one more example. Here can we grant the request 330 by P4 can be granted or not? Let us check the same example. So now the available resources are 332. Now P4 is asking for additional resources 330. So suppose when we allocate 330 for process P4, so what will happen? From the list of available resources 332, we are subtracting 330, then the available resources will become 002. So 002, then with 002 we cannot execute any other resource, any other process. P4 requires maximum 433 resources, P4. So from 433, we are granting we are granting 330. When we grant 330, the allocated resources will become 332, and the need of the resources will be 330 minus 101. So 101 is the remaining resources needed by P4. Now currently available resources in hand is 002. Now when we see the execution sequence from P0 to P4, 743 are the required resources for P0, but available is 002. With 002, 743 cannot be satisfied. P1 requires 122. 122 is greater than 002. So P1 also cannot complete its execution, cannot start its execution. P2 requires 600, so insufficient resources. P3 requires 011. So for P3, the resource C is available, but whereas resource B is not available. So P3 also cannot start its execution. P4 requires 101 resources, but available are 002. So P4 also cannot start its execution because of insufficient resources availability. So granting of the request 330 to process P4 is making the system enter into an unsafe state. So this leads to a deadlock state. So therefore, allocation of the resource 330 for process P4 is denied. So request cannot be granted. Now this is another question. Can the request for 020 by P0 be granted or not? We want to verify this. So with the same example, whatever example we have seen, so this is the allocation matrix, maximum number of required resources, need of the resources, and availability of the resources. So initially 332 resources are available in the system initially. So P0 is asking for 020. So when we subtract 020, the remaining resources will be 312. So when we subtract 020, P0 requires, and how many resources are in need of P0? Let us verify with the original problem. In this problem, 743 is the required. 743 is the required resources by P0. After allocating 020, the need of the resources will become 723. That is what here it is given. The need of the P0 process is 723. Now the available resources are 312. So with 312, can we start execution of the processes? Let us verify from the P0 to P0. So first we take up the least required resources process. So P3 we are considering. P3 requires least number of resources. So 011. So 011 is allocated to P3. So from the list of available resources 312, 011 is subtracted, available resources will become 301. P3 will go for execution, it will release all the processes, all the resources 222. So now the available resources are 523 in hand. Now with 523 we can satisfy the request of P1. P1 requires only 122. So 122 are allocated to 523. The balance will become 401 after allocation of 122. P1 completes its execution, it will release 322 resources. So 322 were released. Available resources are 723 now. So allocation for P2 is carried out 600. Now balance in hand is 123. P2 completes, it will release all its resources. 902 are released, 10 to 5 are in hand now. Now P0 will take up the execution. 723 are the required for P0. So it is allocated. So balance in hand is 302. After P0 completes, it releases 753 resources. So available resources will become 1055. So next P4 is carrying its execution. Need is 431. So 431 is subtracted. 624 are available. Now P4 completes its execution. 433 will be released by P4. And finally the total list of resources 1057 will come back to the system after completing all the processes execution. The execution sequence is P3, P1, P2, P0, P4. So therefore the request for P0 020 by P0 can be granted in this case. Next concept is deadlock detection and recovery. In this scheme, the system will allow to enter into a deadlock state, and periodically an algorithm is invoked that searches for a cycle in the graph. If there is a cycle, there exists a deadlock. Then once the graph is identified, cycle is identified, then we will apply a recovery scheme to break the deadlock cycle. So the idea behind the deadlock detection and recovery is, let the system enter into a deadlock state. Until that, we keep on allocating the resources for the processes without need to check any condition, whether the system is safe state or unsafe state. We don't bother. We keep on allocating the resources to the process. Suppose at one particular point of time the process will become standstill and no process will start its execution because of insufficient resources, or resources may get exhausted but processes will be in a waiting state. So that is called an unsafe state. Once that unsafe state is reached, so we check whether there is a cycle exists in the system or not. Once the deadlock cycle is identified, then we will apply a recovery scheme to break the deadlock cycle. So how frequently we verify for the cycle all depends on the operating system. Now let us take up one example how this deadlock detection is carried out in this deadlock detection recovery scheme. So here, for example, these are all the allocated resources. These are the requested resources by the process. Now the available resources are only 0. With 0, can we complete its execution or not? Now first we will take up P0. P0 does not require any resources. Whatever it needs, it is available already. So P0 starts its execution. So when P0 completes, so it will release its resources. So now the available resources will become 000 plus 010, that becomes 010. Now P2 will start its execution. It releases 303. So when P2 completes, 313 are the available resources in hand. So P2 also completes. Then P3 will take one resource from A and it will start its execution and it completes. So P3 also completes. Then P4 will start its execution and it will complete. So 020 will be released. Okay. So then after releasing whatever resources by P4, then P1 will start its execution and it will complete. So like that, all the processes will complete its execution and then the system will be in a safe state. Coming to another instance of the same multiple instance problem. Here P2 is requesting an additional instance of type C. So P2 is asking for another resource, but available resources are 0. Now consider P0 wants to execute. P0 after executing it releases 0, 1, 0. So the available resources are 0, 1, 0. So next process, which process can start its execution? P1 requests 202, but available is 0, 1, 0. It cannot. P2 requires 0, 0, 1. So available is 0, 1, 0. So P2 cannot start. P3 requires 1, 0, 0, but available is 0, 1, 0. So P3 also can't start. P4 requires 0, 0, 2, but available is 0, 1, 0. P4 also cannot start. So no other process including P2 cannot start its execution because of insufficiency of the resources. Only P0 completes its execution. Remaining processes will not complete its execution due to the insufficient resources. So therefore, additional instance of type C by process P2 is making the system enter into an unsafe state. So deadlock exists. So after finding whether there is a deadlock in the system or not, then we will apply deadlock recovery technique. So allow the system to allocate the resources, periodically check for the deadlock using wait for graph. After recovery mechanism to apply recovery mechanism to break the deadlock cycle by selecting a victim process. How do you select a victim process? The first technique used is when the system is in deadlock, abort all the processes detected in the deadlock cycle. So that is one technique used in the deadlock recovery. So instead of aborting all the processes, we abort one process at a time until the deadlock cycle is eliminated. So this is the second technique. So for example, I take up this graph. In this graph, there is a deadlock. P1, P2, P3, P4, there is a deadlock. First we abort P1. If you abort P1, this loop is eliminated. So P4 will go for execution. Once P4 completes its execution, P2 and P3 will also start execution one after the another. So therefore, the system will enter into a safe state once P1 is terminated. So in that way, one process at a time is terminated until a deadlock cycle is eliminated. So if one process does not eliminate the deadlock cycle, next choose another process to terminate. Like that, third process is terminated, fourth process is terminated. Until the deadlock cycle is eliminated, we abort one process at a time. Then, which process should we choose to abort? There are so many techniques are followed. First one is priority of the process is taken into consideration to abort the process, because when a low priority process is there, high priority process is there. So we always choose a low priority process to terminate. So therefore, low priority processes will encounter starvation in this approach. Next one is how long a process has completed, how much longer to complete. Assume that there are two processes are there, P1 and P2. P1 completed 80% of its execution. P2 completed only 20% of its execution. Then in this case, P2 will become the victim process. So resources the process has used. For example, process P1 used precious resources like CPU, memory, etc. Process P2 used less precious resources like secondary storage, some IO operation, something like that. So in that case, so P1 will be a precious resource, we can hold it, and P2 can be aborted. So this is one example I am telling. So it may be in the other way also. It depends on the system. So how many resources a process needs to complete? So for example, there are two processes, assume P1 and P2. P1 needs 10 more processes to complete its execution. P2 requires only 2 processes to complete its execution. In that case, we terminate P1 process. How many processes will be needed to be terminated? For example, if you terminate process P1, assume that 2 resources will be released. If you terminate process P2, assume that it releases 8 resources. So in that case, if you terminate P2, you get more number of resources left available for remaining processes to complete. So in that case, we will use how many processes will be needed to be terminated and how many resources we will get from that termination. This is based on this. Is process interactive or batch? Interactive processes are interacting with other processes or else interacting with the end users. So interactive processes are assumed to be more precious than batch processes. Generally batch processes will execute in the background. So therefore, if there are two processes, one is interactive process, another one is a batch process, then the choice is batch process and batch process will be terminated. So in this way, the victim process is selected for eliminating the deadlock in the wait for graph. So generally, the selecting a same victim process like a low priority process always makes the process to enter into a starvation, and rollbacking to the previous state and restarting the processes from that particular state is another technique used in the deadlock recovery. Next concept is deadlock ignorance. The deadlock ignorance is nothing but allow the system to allocate the resources. Deadlock ignorance uses the Ostrich algorithm. Ostrich generally stick its head in the sand and pretend there is no problem at all. This method of solving any problem is called Ostrich algorithm. This Ostrich algorithm is the most widely used technique in order to ignore the deadlock, and also it used for all the single end user uses. Because handling the deadlock prevention techniques are more costly than ignoring the deadlock. They put more restrictions on the process. That is the reason we ignore the deadlock and let the system to enter into the deadlock state. Then we will apply some technique for recovering from the deadlock state. If there is a deadlock in the system, then OS will reboot the system in order to function well. The method of solving any problem varies according to the people. So that is the technique used in the deadlock ignorance cycle. The advantage of ignorance is it is simple and the performance is also more, because simple in the sense that the design and implementation of operating system need not worry about how to implement the deadlock prevention techniques. So therefore it is more simple than the avoidance techniques. Performance also, system improve its performance because there are no consumption of significant resources for handling the deadlock prevention techniques. Disadvantage of this deadlock ignorance is unpredictability, because it may lead to unpredictable behavior, making the system less reliable and stable. Sometimes system also will get crashed due to the non-availability of the resources, and processes also blocked. Reduced availability. So deadlocks can cause process to become blocked and reduces the availability of the processes. Thank you for watching this video.